Okay, so for today's class, actually, we will just go to some introductions of a new chapter. Okay, but before that, because our midterm, okay, because our let me write here, midterm is our midterm is 29, right? It's actually the original or default this around, I think around 16 from university, right? So if we compare with the final exam in our schedule, in the university schedule, this is around 10th of January. But because we have late midterm, okay, so this is late midterm. So maybe okay, if we don't finish on time, we will have a late midterm. So maybe late midterm, late final. Maybe around. I hope this around between this January. Okay. So we will have 3 or 4 days late. So I hope you understand this situation. Okay, but I hope. Okay, Okay, I hope we can finish on time. But if not, then we will have a late final exam, 12 to 14 of January. Okay. Okay. So again, this QR code. Please scan the QR code. And again, I'm really sorry for today's class. For those of you who just come to the class. Okay. 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 I think everyone mostly done your scanning the QR code. Okay, so for the final exam, probably we will have a late final exam, but I hope we can finish on 10th of January. Also, I would like to know your opinion. Okay, your opinion about the midterm. Okay, it's hard. Okay, yeah, opinion about midterm. How about the time? Is it enough? Enough time? No. Okay. Uh. Okay. Enough. Okay. Because sometimes, even though I give a lot of okay enough. Okay. Sometimes if I give in like a longer time, if the students are um, if we think that we don't really have, yeah, sometimes like we give, I give the students like, okay, I give you more time, but still if you stuck on some questions, it will be like not necessary you need to have a longer time, because it's already been difficult for some students, right? So yeah, this is what I mean with time is, if you have a like a longer time, maybe you can do better. But sometimes it's not necessary, because the quality or the content of the questions itself, it's maybe it's hard or difficult, so it's not necessary to have like a longer time, right? Okay. I will give you some survey maybe next week about our midterm. Okay, but hopefully we'll have a good statistics. Uh, uh, my score, it will be based on um, I mean the grade. This will be based on statistics. Okay, so I will find the average, and I will find the the passing grade. And in some cases, my passing grade will be different from the grade that came from university. Usually, the passing grade, the standard is, I think, around 60 something. Okay, but in my class sometimes maybe it will be lower than this, maybe 55 or 56, 57. It depends on the statistics. Okay, but it's not too far, not too far. Okay, and how I grade like the final score in your transcript, like A, B, C, blah blah blah. This, it depends. Okay, and it's based on statistic. I will take the normal distribution, and I will find this. This is, I think, from D to C minus. This is from A plus, and this will be from C to A minus. This will be around yeah, this is around BB. But sometimes it's also different. Maybe a lot of C plus here, or maybe a lot of B here, B plus, or B minus here, and B plus here. Depends. Okay, but usually this will be how it looks like, and the one who gets the good score will be around here, and the one who are fail maybe around here. But again, it depends. Okay, it depends on our progress, our statistics. Okay. Okay. Okay, and the midterm, I know it's difficult, but it should be difficult to check the uh, the understanding of your study. Okay, so I hope that that's still okay. But I will do some survey next week. Okay. Okay. Now I would like to start our lecture today with a new chapter, that is the integral. Okay, let me make this. Okay, so if you take some random functions like this, okay, and we are observe the interval a and b, okay, and we look at the functions between this interval, and we take some line here, we also take a line here, and we have some S region. Okay, we have some area of region inside here. That is, we want to observe. Okay, we want to observe. We want to calculate. We want to compute this area under the curve. Okay, so mostly the problem in our half semester will be about this under the curve. Okay, how we are going to find the area of this region here that is under the curve of y equal f of x. Okay. I think, yeah, for today we can finish the introduction part. Okay. Okay, so if we focus here, and we are going to configure something, how to compute this area. Okay. Maybe we can take some approach like this. Okay, and if you look here, there will be some geometric, right? Some geometry. If we have or if we use just a rectangle here, okay, I think rectangle is easy to follow. Okay, it's not difficult geometry. So if we have this green rectangle, okay, even though this rectangle will have some gap here, right? This is the gap between the rectangle and the curve. I think we still can use this rectangle to approximate. Okay, to approximate. So if we have the rectangle like here, so we will have, this is the height, and the height is based on the y, right? The y is f of x, right? So this height will be the f of x, and in between this width will be just the delta x. Okay, right? And we are going to compute this, and we plus the, it depends on how many rectangles, right? Okay, and if we are going to start with some functions that we think already familiar with, we can take okay, we take this function here, y equal x squared. It's easy to follow, and we are going to evaluate this. And we are having the, let me check the table. Okay, I think this. Okay. Okay. We can define this as, and for example, we define with the 4 rectangles. Okay, for area first, for area, and then we can make it into a rectangle. Okay. For example, this is the case. Okay, we take the there is, let me mark this with the green color. Okay, so if we look at the rectangle, we are going to have at least two possibilities. Okay, two possibilities. We can have the curve we can have the curve touching this. Okay, touch the right end, or the curve is touching the left end. Okay, so if we look here, the example here is right endpoint. Okay, so this is, we call right and approach, or just right endpoint. Okay, right endpoint method. It will be different with the left endpoint. The difference is on the results, usually the results. Okay. Okay. If we take the calculation for the, let's say the area, we call R4, right? And then we have 4 rectangles. And if we compute, okay, if we compute, this will be, let me check here. All this delta, this is 1/4, right? 1/4, 1/4, 1/4. Okay. So, and this is the x squared. Okay. So x squared means the 1/4 and then squared. This is, for example, this point here is 1/4 squared. This point here is half squared. This point here is 3/4 squared, and so on. Sorry, not this. This. Sorry. Okay. So we can compute with the 1/4, 1/4 squared. This is the first rectangle. And then plus this, the last one here is 1 squared. And we got the R4 is, if we compute this, okay, if we compute this, this will be resulting 0.46875. Okay. Now, if we take the left endpoint, let me draw this. yeah, more or less is hope you guys understand. Okay, this is the left endpoint. Okay, so if you look at this, is touching the left part here. Now this will be it should be 1/4, but let's say this is 1/4. Okay, 1/4, a half, 3/4, and 1 here. Oh, this is not necessary. Okay. So we will have, if the area is the L4, then this will be 1/4. And if you look here, there is no rectangle at this point here. So we can just multiply with 0 for the first one. And this will be resulting 0.21875. Okay. Now, if you look here, okay, let's say we observe this right endpoint. This right endpoint, it has okay, for the right endpoint, it has this additional area, right? Okay. This additional area means that we want to have this area, right? This is what we are going to approach. Okay, so our goal is to approximate area under the curve. Right? So we want to check this area below the y equal x squared, right? And the first approximation we have this additional area, right? This is additional area. Okay, and when we have the left endpoint here, we have less area. We have less area here. Okay, so actually, our goal is if we want to find the area under the curve, that will be between this number and greater than this number. Okay, so our area, this ideal area, is between the right endpoint and left endpoint. Okay, so probably in the middle. Okay, so probably around 0.3 something, right? So how we can take the approach of that? If we take the same curve and we take with different rectangles, let's say we have maybe 8 rectangles. Let me check. Okay. If we have this, let me make it bigger. If we have using, let's say we have 8, n is 8. Okay, this is also n is 8. We have this is 8 rectangles, and this is 7 because the one that is here actually. Okay. Now, if we look, we still have this is less area here, right? And we also have the additional area here, right? So I think we still have some. So if we write the area is if we calculate the 8 rectangles here, this will result 0.3984 something, and the left endpoint is 0.2734 something decimals. Okay, and the area is still in the middle. But if we compare with the previous calculations, look the number from 4, 6, and 21 here, it became 39, right, and 27. So it's getting closer to some number in between. Okay, it's getting closer. So from 0.46, it become 0.39. It's getting lower, and from 0.21, it's increasing to 0.27. Okay, and it's getting to some number, and I think still we have 0.3 something in the middle. Okay, and we want to know how much decimals we will have. Okay, and the more error, the less error, the results will be more ideal. That's our goal, right? Okay. If we take the let me make a new page. Okay, if we take the make it bigger. Okay, let's start from the first one here. So this is the right endpoint, and we will have the n, or the rectangles that we are making, is 10, 30, and 50. Okay, and then we see the results. Okay, this is having 0.385, and the results for 30 is 0.3502. So it's getting closer to the number we are going to have. And look here, from this additional here, we are going to see that this is becoming more smaller, right? And the rectangle that is here is getting closer to the curve, right? It's getting closer to the curve. And if we have 50, this taking 34, 34, 34. And look at this. Even the left bottom here, because of the pixels, you see that it is almost the same as the curve, right? So I think if we have more, maybe 100 or maybe 500, it's getting really small, and the rectangles become very smooth, right? Okay. And similarly, when we have the left endpoint, if you look here, we still have this less area on this space here. We still have space, a gap between the rectangle and the curve, and we get the 285 for n equal 10. And if we increase the n, let's say 30, we have 0.3169. And look here, the area here becomes very small, very small. And again, it's getting closer to the curve. And if we increase once more, it's getting smaller. And again, it's getting very smooth. And especially if you look at this area here, it's getting similar with the curve itself, right? So same thing, if we increase this into 100 or 200 or even 500, we will get smoother, or the rectangle will be getting closer to the curve. Okay. Okay. Now usually, okay, for the right endpoint, because we have additional area, we call this is overestimate. And this is underestimate. Okay, now, okay, because we already know that if we increase more rectangles, we will have uh, closer results to what we are going to observe with our goal, okay, the ideal area under the curve. Then we can take the let me write into new page. We can take the, let me draw. Okay, let's say this is y equal of x, and we compute from A to B, okay. And we are going to slice this. Okay, we can slice, and let me just slice randomly with the same width of rectangle. And not really the same, but yeah, suppose this is the same width, okay, and we are going to name this one is S1, S2, S3, and we can name with some SI until Sn very end. Okay. So the width of interval is based on the subtraction of b minus a divided by how many rectangles we have. Okay. Or this is we call this the delta x. Okay. So if we name the, okay, if this is x0, a, this is x1, x2, x3, and maybe here is xi, this is xi minus 1, and this is the n is xn, the b, before b is xn minus 1. Let me write here. Okay, now let's see the rectangle. We divide and becoming interval from x0 to x1, x1 to x2, and until it is xn minus 1, xn. Okay. And based on our definition with the delta x, we can take the x1 as a plus delta x, right? We can take also x2 as a plus 2 delta x, okay? If we look here, this is what it means. So this is delta x. This is also delta x. And you see that it is 2 delta x for x2, and then for x3 it's 3 delta x, and so forth. Okay. And we will have xi a plus I delta x. Okay. Now, the area or maybe the area is sum of rectangles, right? And we can write, if we write as Rn, then this will be f x1 delta x plus f x2 delta x. Let me make it a little bit. Let me make it going to left a little bit. Okay, maybe here. And until some xn. That will be the area. And imagine that if n getting to infinite number, getting larger, larger, and larger, really, really large, then the area will be limit as n approaching of infinity. This will be let me write here. Oh, let me write one by one first. Okay. So now we are going to, again, we need the concept of limit, okay, to understand this subject, right? And to understand that we can compute this area under the curve with the help of limit. And instead, okay, we are having, this is the right endpoint, right? If we have the L, the left endpoint, the result probably will be limit as n approaching infinity of the Ln, or this is the area. And for the left endpoint, the differences is if this is started from x1 for the right endpoint like that. If we have the left endpoint, it starts from here, right? From the x0. So we start from x0 instead of the x1. So we have x0 delta x plus and the n here is x n minus 1, right? If we are looking the graph that we are going to have, this is the left endpoint will be here, okay, instead of the right endpoint, this one. Okay, I hope you can see the differences. Okay, so we have until there. Okay, but if we think slowly here, this one is right endpoint, this one is left endpoint, and based on what we have done before, the results will be the right endpoint will be overestimate, the left endpoint will be lower estimate or underestimate, and our goal is in between right endpoint and left endpoint. Now, let's just use sample points. Okay, we call sample points. Okay, so it's not left endpoint or right endpoint. So in one rectangle, so let me draw the rectangle here. If this is the left endpoint, and this is right endpoint, we can have a sample point in between left or right, and it can be anywhere in between left or right endpoint. It can be here, it can be here, it can be here, it can be here, as long as it is between left or right. But it should be consistent. So if we have this, if it is here, then it should be around here, should be around here consistently. Okay. And we call this as a sample point. And this is to avoid we are having an overestimate or underestimate. Okay. We call the number the point. Usually we are writing with some asterisks like that. Okay. So the area, if we are using the sample points, the expressions become okay. Now it's more general. Okay. We are not depending on left or right. Okay. Okay. But actually, aside from left and the sample point, we can also have something called the midpoint. Okay, and let me write that part, and then we can continue to this area here. Let me write first the midpoint. Okay, so we have also midpoint rule. This is written using we call the xi, and then having a dash or line like that in the top, and this is precisely the middle part of the rectangle, precisely. So if this is the rectangle, maybe one, the middle one here. So this will be the xi. This is xi minus 1. This is xi. And this is the midpoint. Okay, we can also have this for our calculation. Okay, but for our proof, we can just use this sample point. Okay, now back to our area here. Okay. To symbolize the sum, this calculation here, the addition here, we are going to use a sigma notation. Okay, sigma notations. Okay, this is called the sigma. Okay, and let me write, I think, in this page here. This is just an additional notes for midpoint rule. We will go back later. So we are going to have a sigma which means this is actually f x1 delta x plus f x2 delta x and f x and delta x. Okay, this is sigma means that from some order of n, that is from 1 to some number of n, how many n we have, we can take the approach, and if we have this is the computations, then we have x1, x2, and until xn, and then we plus all these terms, okay, and that it is this summation. Okay. So we can also write the sample points become with an asterisk like that, and this will resulting this. Okay, the same expression. Okay, and we have some additional or some notes, but I think I cannot really explain or elaborate more, but I think I would just showing you first. That is, okay, so this is notes for sigma. So if we have this sigma 1, okay, this is becoming this n. Okay, if we have this is I, this is actually 1 plus 2 plus 3 plus until n, or if you remember, this is n plus 1 divided by 2. Okay. And if you have n and we have I and a squared, this will be n plus 1 2n plus 1 divided by 6. And if we have cube, this becomes n plus 1 divided by 2, and the whole thing will be squared. Okay. And if we have, let me write here, a constant, c is a constant. This will be c and then a, and then this means a1 plus a2 plus a3 blah blah blah. And if we have take this, come to the left. We can also separate this. And this also happens for the subtraction. Okay. Okay, this is just for notes. And let me tell you later what will we have and why we need this some of these calculations, because this is actually how the computation in integrals will be. Okay. Uh, let me write later in the new page. Okay. Okay. Okay, let me write in the new page. Okay, if you want to take some notes, let me know which part, and I will go back. Okay. Okay. Now, actually, what we are going to have is uh, our definitions. Okay, our definitions. Okay. What we have from let me show you here. What we have here is our definition of area under the curve, or in this case, this is the integral. Okay. So the integral, we may have to approach. Okay, we have first is with the intuition. We know that integral, we can say that that is antiderivative based on our knowledge of derivative. Okay, if we think the derivative will have some form before it's been derived, that we call the antiderivative. Okay, in our intuitions, that is our antiderivative. And based on our approximation with the geometric approach, right, with rectangles, right, and so on, we have this a definite integral. This we can also call indefinite, which means that the definite is having a fixed interval. We know how to compute from A to B, right, the interval. While the indefinite integral, we don't really have any specific interval. Okay? Now, for the first step here, we are going to define this definite integral based on what we have done with our rectangles. Okay, so first is definition of definite integral. Or this is integral from a to b of f of x dx. Okay, so this means that we are going to compute area under the curve of f of x from interval a to b. Okay, so if f is a function defined for interval a to b, and we divide this interval into subinterval of equal width, the base of the rectangles is equal with the delta x, that is b minus a divided by n. And if we let the x0 is a, and then x1, x2, and then xn is equal b, and also let the x1, x2 with the asterisk like that. This is p any sample points, and we say that xi with the asterisk, the sample point, it lies in the some in any subintervals in between of xi and xi minus 1. Okay, I think my words is too big. Let me make it smaller a little bit. Make it smaller. Sorry, so make it smaller here. Okay. Okay, then definite integral of f from a to b, we will have integration, or maybe we can use the blue color, maybe dark blue. Integrations from a, b, f of x dx is equal limit as n approach infinity, and we are using the sigma notations to denotes that this is a summation, and that's the definite integral. And this provided the limit exists, okay, of course, and gives the same value of all possible choices of sample points. And thus, if this exists, then we say that the functions is integrable on the interval AB. Okay. Okay, so that's the definition. Okay, let me make it from here. Okay, any questions first? Okay. So this is the definition, okay, of the definite integral. So the definition here is we are using the concept of the summation. So let me give you example on how actually the computations looks like. Okay. Okay. Let me write first the evaluate. Okay. We start from like a simple one. I know that we can integral if we use the knowledge from previous, like maybe you already learn the integral, and we know that if we want to have an antiderivative of um, each element, and we can have this 1 over 4 x with 4, and also we can have 3x squared, and we evaluate from 0 to 3, and we can compute and we can get some number, right? But I want just to show you here what is really happened in our computations, okay? In our calculators, in our any computation software, what is really happened. Okay, so by definition, we going by the limit. Start from this summation. Okay. Now our f of x is x cubed minus 6x. Okay. And AB is from 0 to 3, right? So delta x will be 3 over n, b minus a over n. And our xi, the sample point, will be 3 I n. Okay. Now we are going to start to write from the definition here. We are using the summation and f, and we are going to use the x will be 3i over n, okay, and the delta x is 3 over n. Okay. Okay. Now we can compute this, and we can factorize the 3 over n outside of the summation. So we can have limit and we can use the functions that is x cubed. X cubed means that we are going to take cube for this 3i over n and minus 6x. Okay. Okay, let's start to compute this. And this will be 27i cubed divided by n cubed. And this will be 18i and then divided by n. Okay. Okay, now we are going to remove, okay, we are going to remove this 27 and n cubed and this 18 and n. Okay, we are going to move outside. So we may have two different, let me write first, maybe here. So this is 3 over n. Let me use the bracket to avoid mistake. So this is 27 and cube. This is I cube, and then this will be, over n. This is I. Okay. Now let's multiply this to here. Okay. Let's multiply, and the results will be, let me write. Maybe I will move this to left so I will have some space on the right. So this will be limit. This will be 81 over n4 sigma, and this will be 54 n squared. Okay. Okay, now with our knowledge of the nodes before, okay, I haven't elaborate more about that, but let's just use that as our calculation here. So sigma of I cube, it's become n plus 1 over 2, and then squared. And this will be, I will be just n plus 1 divided by 2. Okay. Okay. Because we have n4 here and n squared here, my idea is we are going to exchange this to this 2. Okay. And the same way, we are going to exchange this into here. Let me use the different color here. So this one will be n plus 1, and this will be n squared, right? Because it is having squared on outside, right? And this is becomes n plus 1, and this is n squared, okay? And if we take this calculation, this become n squared, or we can have 1 plus 1 over n. Okay, and then this is squared. This is also squared. Same thing here. We are going to have n squared plus 1 divided n squared. This is 1 plus 1 over n squared. Okay. Oh, sorry. This is 1 over n. Because this is n squared plus n. Okay. Okay, now let's just take the calculations and write here. Let me write here a limit. So this is 81 over 4. And the inside will be 1 plus 1 over n squared minus 54 over n squared. And this will be 1 plus 1 over n. Oh, sorry, not n squared, because it's already changed to 2. Okay. With the limit, if we check limit here, check limit there, and it's perfectly becomes 0, right? It becomes 0, it becomes 0. And we are having the 81 over 4 minus 27. And it will be resulting negative 6.75. And I think if you check the results here, it's also the same, negative 6.75. Okay. And if we take the graph of the function, let me write this and make some additional graph here. and this is from 0 to 3. Okay, if we look here, okay, if you look the area below and the area that is above the x-axis, okay, if we have this graph, okay, and we want to know the area under the curve, okay, what area under the curve means, okay, what does that mean? So let me write here, area under the curve, what does it mean? Is it supposed to be anything that below the curve? So if I have this curve like this, okay, if we are translate the area under the curve literally, then this will be the under the curve, right? This part here, right? But that is not what it means. Okay, it's not what the area under the curve means. Okay, so if we have the situations, okay, then area under the curve means that this is actually we are compute the x-axis to the curve, the distance, okay. Area between, let me write, it's better. Area between x-axis and f of x. I think that will be a better understanding. So this is the x-axis, the middle one. And your area under the curve means that the area between this x and the curve, okay, and which is the green color here and the red color there. Okay, and because this green is below 0, that is negative. So this part here, the area will be negative area. And this area here will be a positive area. Okay. So that's why we have this here, negative 6.75. If you look at the area, the green area is larger than the red color, right? And that means that it is going to have a negative results. Okay. 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 Let me continue a little bit to some property that we might have and will be also necessary in most integral. Okay, let's start. So some property. Okay, if we take the integral, the same integral, but the interval we are switching from b to a, this is actually the same as a negative part of that integral. Okay. If we take another integral, if we have the same interval from a to a, which means that we are going to subtract the area by itself, and it will be a 0. And if we have from A to B, and we have a C, C is a constant, then this will be resulting B minus A like that. And if we have another one from A to B, if we have two functions inside, we have some addition plus, and this is bx. We can separate this and if we have A, B, and C is also constant, we can factorize C. And if we have A, B, fx dx, we can still separate this. Okay, we have another constant or another point C that is in between A and B. Okay, so if we look here, like from the previous one here, our computation is from 0 to 3. But we may have another one here, maybe, that is maybe something x there. And we can take the 0x and then fx dx, and then plus from x to 3 of another one, let's say, it's still the same fx dx, right? Same functions. Okay. Because you see that it's perfectly taking two area, right? The area that is negative and the area that is positive. So this is the property, the basic property. I think I combine into one. Okay. Okay, I hope you guys really take some notes from here. Let me move to another page to give you some another property. We call this property is the comparison properties. Okay, first, if f of x is greater or equal 0, and a to b is the interval, then we say that if we have integration, this will be also resulting positive integral. And if we have two functions, f and g, and f is greater or equal g, and it is the same at the same interval a, b, if we take integrations, the f will be greater than this g. And if we have some m, small m like this, at the same interval a, b, or if we have in the graph, let me draw the graph. This is M, this is big M and small m, and in the middle we have our our function. And we can take this into our integrations. That we state that the integral is in between these two values. And let's say this is the A, this is B. Okay. 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 Now from this comparison, okay, I hope you get the point here, okay, the comparison here. This is actually, we are taking the integral AB, integral AB, integral AB, and this is the results. Okay, the comparison theorem. It's similar to the squeeze theorem. The squeeze using limit is comparison using an integral, okay? And we will see the link later from the squeeze and this integral comparison. Okay, we will see at this at later later sections. Okay. Okay. Now let's make the some function here. Just random function. Let's say this is A. Sorry. And this is B. Okay. And in between, let's say we have some X. Okay. And let's change this x-axis into another variable t. Okay. And we have the area just until the a to x. Okay. And let's name this with the g of x. Okay. So g of x is an area from interval a to x, and we are going to write as g of x. This is the area that we are going to look at the under the curve, and this will result from a interval from a to x. This x of our, this is the function of t, okay, for this t variable. So f of t dt, okay, where f is continuous function on interval ab, and x varies between a and b. So which means that the area, this area in between of AB, this area, or we call this G, this is dependent on X. So this is a function. So we are going to have a dependent area, or this is a function. Okay, because if we change the positions of X, the G will be also changing. So we are making this area as a functions. Okay, and we can have the expressions f of t dt, okay, for the G from A to X. Okay. Okay, now we are going to link. Okay, we are going to link because the calculus is based on derivative and integral, right? So we are going to link this together. Okay. Okay. I think because in the previous antiderivative, we already have the big F. Okay, let's just change to this F. Okay, but if you already write G, that's okay. I mean, make notes here. That is if we have this, let me write this is we call also the antiderivative of F, right? And F is differentiable on AB. Okay. Okay. If we take this, if we take this first derivative, okay, this will be, let me just write the dx of the left part here, okay, this will resulting the small f x, okay. And from this point of view, from this perspective, we can say that every continuous function small f has antiderivative big F. Okay. And this is concludes that this is what we call the fundamental theory of calculus. That links the derivative and integral. So fundamental theory of calculus, FDOC. Okay. Okay. This is the first one. The second one that we can have conclusions, that is, if this f is continuous on this interval AB, then we can also write this integration of f. It can have the antiderivative b and then antiderivative A, where this f is antiderivative of f, where this big F prime is equal F, or we can also see from here F prime F. Okay. Oh, so these two concept or two statement that is the principles on the fundamental theory of calculus. I will give you some proof on how we are going to state that, okay, this is true by our knowledge from derivative, knowledge from the limit, and we can have the proof. Okay, let me write the proof. Okay, and I think that will be the last sections. And I will review on Monday what we learned today. This is just a brief intro from 5.1, 5.2, 5.3. I'm squeezed all together, and I will give you another point of view later on Monday. So I hope this is just getting to know what is integral about. Okay. Okay. Suppose f is continuous on interval AB. Okay. And if x is in between A and B, if antiderivative x is equal let me write the statement first, and then let's prove the statement. Okay, this is what we write before. Okay, and we write the f is continuous on interval AB, differentiable on AB, and if first, if x and x plus h, so we adding h to take proof on limit and integral on interval AB, then if we take this f antiderivative x plus h minus antiderivative x, this is, we can write a and x plus h antiderivative of this is ft dt, and this is integral from a to x ft dt. Okay, so we start from these expressions that is based on our statement. Okay, now if we look here, we have the x plus h, a, so the interval is from a to x plus h. So if we are going to look at the interval, this is a, b, and this is x, and maybe this is x plus h, right? Now I can separate these integrations. Okay, I will separate this, become ax and x plus h. Okay, so this is 1 and 2. So the first one becomes a x ft dt plus x plus h ft dt. Oh, any questions? Any questions? Raising hand. Oh, okay. Oh, Oliver, you asked before. Can you give us an example of a limit has same value? Actually, that is the statement, Oliver. So that means that for all possible choices of sample points, if we are using the limit as n approaching infinity, the results should be the same. So we say, and we compute that the integral results will be the same for all possible sample points. That means that our limit as n approaching infinity, that will be getting same value. Okay. I think the sample points is how to choose the sample points is another subject in approximations. Okay, that is we can use the especially we learn about left endpoint, a right endpoint, a midpoint rule. I have talked before. Later we have also another one like trapezoid, and also the Simpson rule later. But that is all for approximations. That is, if we are not having any integrable or differentiable form, like for example, the integral of something that is the function is really complicated, we cannot really solve it through our knowledge of derivative in calculus, then we can solve it through approximations with some summation, and we can take some approach on how many rectangles we have and how many and how we are going to take the sample points. We take to the midpoint, we take to the trapezoid, or we take left endpoint, right endpoint, and the more we are getting a lot of results, we can see which one is approximate to a better number. Okay, and it will be ideal if we have the same value of the sample points, and that will be good results if we choose those sample points. Okay, I hope you get my point, Oliver. Okay. Okay, and continue here. Then we minus this. Okay, so this one becomes 2, right? And then this will cancel this. Okay, so the results will be the whole results is, let me write here. Okay, the whole results, if we take or multiply with 1 over h, both sides, this will be happening. And this is for h is not equal 0. And we assume if h is positive, then and f is continuous on x plus h. Okay, this part here. Okay, to prove the whole thing, we need another theorem. Okay, we need to have another theorem. That is, we call the extreme value theorem. Okay, extreme value theorem. Let me write in the next page because it's a little bit longer. So we need to have, we call the extreme value theorem. So suppose there are, we introduce u, v on x and x plus h, where the fu is, we call m, and fv is the big M. And we call this is a minimum value. This is max value. So this is the similar M with the previous one, in the comparison theorem. So this will be this is the maximum value. Let's say that is big M, and this is the minimum value. And maybe we have like this. Okay, this is just a random illustration. Okay, this is y equal f of x, and this will be M. This will be U and V. Okay, and M, the small and big M is this minimum and maximum value. And based on what we have, we can take this integrations and we can have the comparison theorem like the previous slides. And similarly, if we are going to have interval from x to x plus h, and we have ft dt, okay, and this b minus a becomes the distance of h, okay, and then we are going to multiply 1 over h, all terms, then we will have m, and this will be 1 over h, and this will be just pick m like that. Okay, and we know that the small m here is the function of u from our assumption and definition, and this whole part here is actually, we can write as these terms, right? The antiderivative. So we can write this x plus h and divide by h. This is f p. Okay, now let's use limit. Okay, so let the h is getting closer to 0. So what will happen when h is 0? Because u and v is in between x and x plus h. When h is becoming 0, u also getting closer to x, right? Because this is x plus h. U and v is in between, right? If h is getting closer to 0, then u is getting closer to here, right? Okay, got it? Now, if we take the limit of h getting 0 of f of u, then this limit becoming u getting close to x of f of u, which means we are getting closer to, we can just use this as f of x. And the same thing with this v is also v getting close to x, and this will be resulting the same similar results. And by squeeze theorem in limit, we will have limit as h getting closer to 0 of f x plus h minus of h. This will be resulting this small f. Okay. And you see that this is actually similar results on our limit definition of derivative, if you remember. In derivative, we have limit right? It's similar. Okay. So this is proven that the f prime or antiderivative prime x is f of x. So that if we have integral a b of fx dx, we can take this into this form. And this is the definite integral. Okay, that's the end of the lecture. Okay, so there will be no feedback time today. Okay, maybe next week we will have, and I will end up until here. Hopefully, as an introduction, you get another perspective of integral. Okay, I know some of you already learned the integral before. Okay, Laura, wait a minute. Here. Okay, and again, that is the lecture today. If you want to leave the Google Meet, you can leave the Google Meet, and see you on Monday. And sorry for the trouble today. I cannot come to class due to some circumstances in my house. Okay. Okay. And for the results of the midterm, later I will give to you maybe next week, Friday next week, or maybe Monday next 2 weeks. Okay. If not Friday, then Monday. Okay. And hopefully you get good results. Okay. Hopefully you get good results. Okay. See you next Monday. Yeah, you're welcome, everyone.